Okay, so recording is in progress. Welcome back to Organic Chemistry 2341, section 252. This is our Monday, Wednesday, 12:30 class. We are going to continue on with module 5, which is stereochemistry. We have two types of stereochemistry we're playing with. We're looking at those geometric isomers with things that don't rotate. And we're looking at those four things bonded to a single carbon, and those have sigma bonds and those can rotate. So we actually have to manipulate those to get us to the right configuration so we can assign them correctly as R and S. And luckily, we can also assign our cis and trans or our E and Z with our non-rotating double bonds using the same rules. So we're going to use the same rules for prioritization. It's just we have to do them a little bit differently. Today's activity will involve the first page is going to be R and S. And I'll give you a hint. The first thing you do is find out if it has 4 different groups on it, because there are some of them that don't. And so that you can easily start going down the path of trying to assign it R and S and get halfway through it and go, hey, these are the same. Ah, darn it. So look for that first and then go ahead and do the second half. The second half is all about E and Z. And again, the same prioritization rules we have. We have those 3 prioritization rules: atomic number, not mass, atomic number. If you can differentiate with atomic number, you're done. If you can't differentiate with atomic number, you keep going out until there is something different, and the one that has the higher atomic number on that difference is your higher priority. And don't forget that double bonds or triple bonds count as that atom that many times, however many bonds you have. So if you have a double bond to an oxygen, you count oxygen twice. If you have a triple bond to a nitrogen, you count nitrogen 3 times. So those are our prioritization rules. Let's go back and look at having more than one stereocenter in our system, and we call those diastereomers. Okay, I'm going to go ahead and share my screen. And I'm going to admit the person there. All right, so just to remind you, we have a single pair of non-superimposable mirror image molecules where we have 2 groups switched in space. Okay, those are enantiomers, and they always come in pairs. Okay, so we're never going to see anything but 2 of those. Okay, and if they do overlap, or if they do have 2 of the same groups on there, they will not be able to be non-superimposable mirror images. They will be the same compound, and they aren't chiral. So we need to pay attention to that. But once we have 2 different stereocenters in the system, we have to have now a new type of isomer. We call that a diastereomer. And so it's 2 or more, but the name is diastereomer. And so the idea is that you would have one pair of enantiomers that are your non-superimposable mirror images of each other. Then you would have another set of enantiomers that are a non-superimposable mirror image of each other. And so you would, and if you took one from one set and one from the other set, you can compare those, and those would be diastereomers. The cool thing is that enantiomers they all have the same physical properties, right? So the only thing they do is rotate light differently. But in the diastereomer pairs, actually you can tell the difference between the 2 different diastereomer pairs because they frequently have different properties, different melting points and boiling points, so you can differentiate them. Okay, so for example, if you had a mixture of this pair of enantiomers here, you would not be able to separate them by most means because they have the exact same physical properties. And these right here would not be separable from each other because they would have similar physical properties. However, these 2 probably will most likely have different physical properties, and you can separate that pair. Even because they are diastereomers and they are not enantiomers, they should have something physical property difference between them that you can tell the difference. Okay, so that leads us on to how do we assign these, okay? And by the book method, this is whichever method you use, please use one or the other. Use the hand method or the book method, which is that redrawing of the system here. Either way you do it, what you're going to do is your prioritization, when you view it dead on where your lowest priority is behind, clockwise is always going to be R, counterclockwise is always going to be S. Now, let's assign this pair of diastereomers. The cool thing is, once you have a pair of enantiomers with 2 stereocenters like this, once you assign one of them, you know what the other one's going to be because it's going to be the opposite. If this center is an S, this center is going to be an R. Okay, so the mirror image is going to be the opposite isomer from that. So in this case, if this is an R, the other half of the enantiomer pair is going to be the other one. So we can always just assign one set, and then we can understand what the R and S configuration are on the other set. Now again, using this book method, I'm going to review that right here. We have our lowest priority group behind us here, which is in this case our hydrogen. We have our bromine highest, so that's going to be our 1. We have our carbon here with more than the hydrogens on it, which is going to be 2. Then we have our carbon with our hydrogens on it, which is 3, admitting somebody in from the waiting room. And that is going with the lowest priority behind us. We go 1, 2, 3, that's counterclockwise, and that gives us our S configuration. Okay, remember, you always want that lowest priority backwards. Okay, so okay, so that's how we would be able to assign the R and the S to these, and therefore we also have to put that in our final name, and our final name would be to name the number of the carbon and whether it's R or S, and then number the second carbon and whether it's R and S, and then the rest of the name. So just like a cis or trans or an E or Z, it comes at the beginning of the name, and like an E and Z, it comes in brackets. Okay, so for this particular isomer right here on this side, it's 2S3R-2,3 dibromo-pentane. And notice the other enantiomer is the exact opposite. It's 2R-3S, 2,3-dibromopentane. Okay, so you'll always see that where one enantiomer is going to be the equal and opposite, or the mirror image of the other. It's always going to switch that R and S. Okay, questions on diastereomers. Now I want to get into what we call Fischer projections, because it makes it easier to draw these things and assign R and S if we know where we don't have to draw all the wedges and where we don't have to draw all of the other systems. And so in general, it's going to be the same type of thing. We're going to make a horizontal and a vertical bonds that we have, but they're always going to be oriented in the same way. The vertical lines always represent the, number 1, they intersect at the chiral carbon. And number 2, the ones that are going up and down are always behind the viewer, behind the plane of the paper or the iPad. The ones that are going horizontally are always coming toward you. Okay, so they're coming toward you. Where do you get the 2 and 3 from on R and S? Okay, so on this particular one here, it was carbon number 2 right here. Notice carbon number 2 has the S configuration. So that's where the 2S comes from. Carbon number 3 had the R configuration. So that's where the R comes from. Okay. Sorry, I saw that question in the chat late. Okay, so by orienting our Fischer projections in the same way every single time, we don't have to draw the wedges because it's going to mean the same thing. So whenever we have just a single stereocenter, we're going to have just one intersection, and then we're going to have these ones are the ones going behind the plane, and these horizontal ones are the ones going out to the plane. So from that, we can actually then orient our hand or our configuration, redraw it such that the hydrogen is going back, and assign our R and S. Okay. Now, this is really helpful when you have multiple stereocenters, because then you only have to draw a single line and have all your stereocenters along that vertical axis. Okay, so let's show you that. Okay, so the way we do that is, let's go ahead and convert this 2R3S butane 2,3-diol to our Fischer projection. Okay, now this also helps us because, number 1, they're always in the same configuration. Our chiral carbons are always on that vertical axis, and we now have a way to look for mirror planes to see if we lose stereochemistry or not. Okay, or to see if it is a chiral or achiral compound. So let's translate this first right here. So what we want to do when we translate this is we want to have the longest carbon chain in the vertical axis. Okay, so we want the longest carbon chain in the vertical axis. So what we're going to do is we're going to line up our longest carbon chain such that they're going to point in the same direction. Okay, because on that vertical axis, the ones at the ends are pointing down. So we want to put them in the exact same direction. So in this case, we've just rotated this around such that we have our carbons all in the same plane, and notice they're pointing down so that when we put them onto a vertical axis, so we're going to take this carbon and move it up here to put all those carbons on our vertical axis, it's going to look like this. And notice we're keeping all our wedges here to make sure that we know where things are. Okay, so this OH was facing out before we did the rotation around this bond. That makes this OH go to the back. So that's why we have our dashed wedge here. And we're drawing our hydrogens here because we don't want to forget where they are. We want to make sure that where they are. And since they're not part of the carbon chain, we have to assign them to this area here. So now if you look from the top down, you see the OHs are going to be on the right side. You see the hydrogens are going to be the left side, and we see all these carbons are going to be in a straight line. Okay, so when we look at that, we get this image here. So our carbons in our straight line, and they're going up and down this way here. And notice that because they're pointing down in this formation here, our wedges here are dashed. Okay, so that's a must for the Fischer projection. And so we have those down, and then these two carbons are in the plane of the paper. Okay, so that means our OHs now are both facing up, and our hydrogens are both facing up. So now let's get rid of the wedges and draw it as just a line drawing. So now we can do our true Fischer projection, where we draw it where our line is vertical here. We know that our carbon centers are at the cross points here, and we know that the things on the horizontal sides are facing up at us, so we can assign R and S to the system. Okay. Now that we have that drawn, what we can also see is, remember, when we looked at anything with a plane of symmetry somewhere within the molecule, sometimes through an atom, sometimes through a bond, whenever it had a plane of symmetry, it became achiral and loses optical activity. Okay, so even though this compound has two stereocenters, by the time we convert it to our Fischer projection, we can see that there's a mirror plane, and it becomes a achiral compound. An achiral compound. Sorry. Okay, so does that mean everything we translate into this is going to have some kind of mirror plane? Well, probably not. So let's do the other isomer. So this was the RS isomer. Let's do the RR isomer. That's just would be one of the other isomers. Notice it wouldn't be an enantiomer because we have both, only one of them changing. That means we have one of each of the diastereomers. So these are diastereomers of each other, but they are not enantiomers. Okay, so let's do that translation again. What we're going to do first is we're going to rotate around this bond, put our carbon down, and we're going to view from the top again. And notice the hydrogen and the OH are going to be on the right side, and the OH and the hydrogen are going to be on the left side. And so when we put this carbon at the top here, we have this OH facing out at us and this OH facing out of it, but on the other side of that axis of the carbons right here. And so when we draw it as our Fischer projection, we end up getting this compound here. Now notice it looks very similar to that, except for the OHs, one OH has been moved over. And the benefit or the outcome of having that OH moved over to here is now there is no plane of symmetry. You draw it this way, you have hydrogen, oxygen opposite each other. You have draw it this way, you have OH and hydrogen opposite each other. So there is no plane of symmetry. And so this particular part of the diastereomer is optically active and is chiral. Okay. Now, we have a special name for a compound that has this plane of symmetry and loses its chirality. It's called a meso compound, M-E-S-O, a meso compound. Okay. All right, questions on that? So let's take a look at those two sets of types of stereochemical compounds, the chiral or non-chiral compounds, and let's compare and contrast their definitions. Okay, so just by using our Fischer projection, and notice this is a really good slide to help you understand conversion right here. It starts with the molecule up here again, and you might want to look at this in detail on your own. You do the first thing is you put all your carbons in the row right here, then you convert it to your dashed line, and that converts it to your Fischer projection. You might want to do that a couple times just to make sure you can. And in this case here, we have an S and an S, which means its enantiomer is the R and R. Remember, the enantiomer is going to be equal and opposite the thing, so it's non-superimposable. Okay, so that makes this set here of enantiomers. Okay, so how do we go from the one set of enantiomers to the other set of the enantiomers? The way we do that is we change one of the stereocenters to the opposite side. So let's look at that. So here we started with an S and an S. So to get to one of the diastereomers, all we do is convert one of them. We've converted this S to an R. This S stayed the same. So by that converting one stereocenter, we now have the first of our diastereomers. Remember, we changed it from R to S, so it can't be an enantiomer because they're no longer superimposable mirror images. But you can know that. They're already assigned as S and R on this right here, but we could also go to this right here and assign it. I could use my hand to assign it, and we have 1, 2, 3, which is counterclockwise, which is S. Okay. And if you were to rotate this around, the chlorine would be on this side, the methyl group would be on this side, and the carbon would be here. And that would give us 1, 2, 3, S. Okay. So we have our enantiomers. All we have to do is flip both of the assignments from R to S or S to R. But for diastereomers, we only flip one of them to the opposite. Okay. Now that we have the opposite here, we can draw our mirror plane and draw our other compound. But we know that if we had an R here, we're going to end up with an S here. If we add an S here, we're going to end up with an R here. So now we have our other pair of enantiomers. And these are all diastereomers of each other in the crossway here. But we have our pair of enantiomers, which have the same chiral assignment of S and S or R and R. And then we have a pair of enantiomers where they have opposite. R and S appears in both of the enantiomers. Okay, so you see how they're related, but they are different. Okay. And again, the use of the Fischer projection makes it easier to assign one to the other, because all you have to do is flop your groups to get the enantiomers, and all you have to do is mix one of the groups to get to your diastereomer. Okay, so what if you have more than two stereocenters? Okay, well, we'll just have to assign them, and you have that many more isomers possible. Remember, it's 2 to however many chiral centers you have. In this case, we have 3 chiral centers, meaning we have 8 possible stereoisomers. However, we have to also look for mirror planes. So in this case, it's unsymmetrically, it's kind of done in a way so we probably don't have any mirror planes in them. But notice that when we start to assign these, we're going to end up with all the possible configurations of with an RRS, SSR. So this would be the an equal and opposite version of this right here. So these are probably enantiomers. SRS, so these are going to be enantiomers. these are going to be enantiomers, and these are going to be enantiomers. But this is going to be a set of 4 pairs in their set of diastereomers. Okay, so each of these individual sets are sets of enantiomers because we've taken each center and made it the opposite. So we went from an R to an S here, an R to an S here, and an S to an R here. That would happen in our mirror plane. Each of those stereocenters would reverse. That's how we know that's that pair of enantiomers. And then when we go to the next one, when all the stereocenters convert from one to the other, then that is our second pair of enantiomers. Questions on that? Okay, so you could get really crazy and put 4 centers on there, and then you'd have 16 of them. So, but I'm not going to do that to you. That's kind of mean. But if you're ever doing research, you can actually do that. Okay, so what if you find a mirror plane in one of your diastereomers? Okay, so when you find that in here, we call that a meso compound. Okay, so if you can draw that mirror plane here, that means you can actually take this, rotate it 180 degrees, and it'll overlay the other compound exactly. That's what that mirror plane is accomplishing. It's saying that those 2 compounds are superimposable. If they are superimposable, they are not chiral, and they are a meso compound. Okay, so notice the pair of enantiomers up here, though. We have an R and an R and an S and an S, and we do not have that mirror plane. So they are mirror images of each other and non-superimposable, and they are true enantiomers. And they have optical activity and exactly the same melting point. Okay, by switching one of those centers, and in this case here, we're switching this R to an S, we've now changed it enough such that number one, it has a different melting point. So it's not an enantiomer of the compounds above, but it has a mirror plane and it has 0 optical activity. Okay, so in this case, we only have 3 unique compounds in this set of diastereomers. Okay, so you would always draw all 4 in the set of diastereomers and then look for the mirror plane. If you find it, it's going to turn it into a meso compound. And it is not chiral. It does not have optical activity. All right, questions? Okay. And so this is a review of all of that as well, showing you that in this case, we also can have, we have the dibromo compound here is the one that becomes the meso compound. Again, this is a good chart to go through and convert from the way it's drawn to the reconfiguration to get to your Fischer projection. Draw your Fischer projection with your wedges based on this compound, and then draw it with your lines. And then you can start to assign your R's and S's. Okay. All right. Let's see. I think I have one more slide. Yes. No, we have other slides now. Okay. So the other kind of stereochemical we have is the one where we don't have that rotation. Okay. So we have to look for what's bonded to each carbon on each side of the alkene. Okay. So if you have the same 2 things bonded to the same carbon right here, then you can have diastereomers. Okay. If you have different things bonded to the carbons, for example, here we have a chlorine and a bromine, and here we have a chlorine and a bromine. So that means they have the same 2 things attached to the same carbon. And over here we have a fluorine and an iodine, and we have a fluorine and an iodine. We have the same 2 things attached to that carbon. Okay, that makes them diastereomers because it's the same connections, just in a different place in space. Notice the I and the F have swapped places. The chlorine and the bromine have stayed there. Okay, so that means we have a diastereomer possible with our alkenes as well, because we don't have that free rotation. However, if they're not bonded to the same compound, they become structural isomers. They're not diastereomers because you actually change the connectivity. So here we have a fluorine and a chlorine instead of the bromine, okay? That means it is not a stereoisomer of the one above it because you've changed the connection, okay? Now, and if you took the mirror image of that, it would also give you a diastereomer because this is going to be, I'm sorry, not the mirror image, but you kept the same connectivity here, but you swapped two of the groups in space. Notice these two are opposite. These two are also still diastereomers, okay? But between the bottom row and the top row, those are just structural isomers, okay? So it's a little easier for those alkenes, okay? And again, we're gonna assign the E and Z priority using that same rule of atomic numbers, etc. Okay, so what's really strange is that when you get to cyclo groups, especially ones that are, you know, small, or even like cyclohexanes here, it starts to become harder and harder to see the isomers because of where they are. So for example, if you have just one substitution on this cyclopropane right here, you only have one isomer because no matter which way you turn it or flip it, it would be equivalent to itself. But if you put two different things on a cyclopropane, you actually end up with 4 isomers, okay? So you end up with this 1,1 isomer. And notice that there's no chirality on that because there's no carbon with 4 different things bonded to it, okay? Now, once we get to here, now we have 2 right here that have 4 different things bonded. Oh, wait, they don't have 4 different things bonded to it because they only have 1 here, 1 here. Oh, they have 4 different things bonded to it. And so we call this the Cis configuration because they're on the same side of the ring, okay? Now, if you put one of them on the bottom here, now you actually can get enantiomers because you now can create a non-superimposable mirror image. Notice if you tried to create a mirror image of this cis one right here, they'd both be on the top again. It'd be the exact same compound. So there is no enantiomer on this one. But this one, because one's up and one's down, and the mirror images are not superimposable, because you can you'll line up this part right here, but then whatever the attachment is will always be opposite each other. You end up with a pair of enantiomers. Okay. Now, if you do the same thing on a bigger ring, like a cyclobutane here, you'll end up with only 1 isomer again. But how many isomers will you have if you put 2 substituents on? Okay. So let's draw those out and see what they are in here. The first one is going to be the one with the 2 on the same carbon, right? The 2 attachments on the same carbon. And so we should only have 1 isomer on that because none of these are chiral. And what's also interesting is there's also a plane of symmetry in here. There's not a single carbon with 4 different things bonded to it, and there's a plane of symmetry, meaning that it is a valid isomer, but it is not it does not have chirality. Now, right here, once we do this, now we do have 4 different things bonded to those things, but we have that plane of symmetry. The plane of symmetry, this side looks exactly like that side. So again, it's a good isomer, but it is not chiral. Okay. If we go to our trans, then we can create a mirror image here, and there is no mirror plane available to us. So we do have a pair of enantiomers with that isomer. When we go to them opposite, the 1,3, notice that the switch is over here. In the 1,3 and the cis or the trans, you now have a mirror plane through those 2 that are all facing up the same way or facing down the same way. And even if you drew the mirror image of this one right here, it'd actually flip over and be the exact same compound. So we end up with only 6 of these, but only 3 of them, no, only 2 of them are chiral. 4 of them have planes of symmetry. Okay.
I have a question. For that first one, which are the 4 different atoms? I can't tell.
This one doesn't have 4 different atoms on it. See, because it has 2 X's and then these are exactly the same carbons. So this one does not have 4. It only has 3 different groups in any one space. because we have hydrogens on all of these and we have X's on these two. So that one does not have even a chiral carbon on it at all. This one does. We have a hydrogen, an X, and then we have a carbon with an X on it and a carbon over here with 2 hydrogens on it. So that's the first isomer. We have 4 different groups attached to a carbon. Does that make sense?
Yes, thank you.
Okay. So there's also a way to have a chiral compound without an actual chiral center. And the reason is because it's fixed in space and it has its interesting geometry. And these are allenes, okay? And the reason they're fixed in space is think about where the double bond for this is. So we have our p orbital is going to be out like this to make that first double bond. And then the p orbital is going to be out like this to make that second double bond. So because one of the pi's is in this plane and one of the pi's is in this plane, it's fixed in space. So now we have 4 different groups that are fixed in space. So technically, if all 3 of those carbons together create our chiral center. And so we actually have a chiral compound with without a chiral atom. We have a chiral bond. So the bond between these 3 carbons right here creates that chiral center, but not a chiral atom. And notice if we have the 2 groups on the same side, if we make the mirror image, that's actually just the same compound. It's just a conformer. However, if we put 1 on each side, those bromines are fixed in space. Okay, one's going to be pointing down, one's going to be pointing out at us. And we can create a mirror image that's non-superimposable. So it does have an enantiomer. Excuse me. Okay. Questions on that? So these are weird, but they happen from time to time. Okay. All right, so for the last part of this chapter, let's go review quickly. Structural isomers have different have the same molecular formula, but are connected different ways. You can even have different functional groups with structural isomers. Constitutional isomers are only different in the order of attachment. Stereoisomers are ones that have the exact same connectivity. They only differ from an arrangement in space. And so your stereoisomers can be alkenes, and it can be carbons with 4 different groups bonded to them. Geometric isomers are stereoisomers with different groups on different sides of that rigid double bond. Okay. Chiral is any object that has a non-superimposable mirror image. Achiral is it has a superimposable mirror image. Okay. Enantiomers always come in pairs. Okay. Diastereomers come in sets. You have as many diastereomers sets as you have stereocenters. But once you start having diastereomers, you have the opportunity for a mirror plane, and you have to look for that mirror plane. And if you have one, it becomes a meso compound. And you end up with that set of diastereomers turns into a single compound. And so therefore you can. Geometric isomers would be the allenes. Let's see. Yes, that is true. Okay. And then, of course, this is a visual review of all those things. Okay. Questions on stereochemistry. Okay. Remember, stereo means space. So it's all about the 3-dimensional location in space. Okay, let me go ahead and stop sharing for a minute. Go ahead and start pulling up your activity. And I'm going to pull up mine if I can remember where I put it. Group activity 1, no. Desktop. That's it. Input today. All right, let me go find another copy of it here. Okay, let's find our, there it is. Nope, What's that? Oh, I know where it is. Excuse me. There it is. Sorry, I thought I had this on my desktop, but apparently I do not. Okay, I'm going to share my screen, which is the Adobe Acrobat. Okay, here's the instructions for today's group activity. Go ahead and get something out. Remember that when you get into your group room, you can share like one of your screens, and then you can use the whiteboard function to write on it, and you can all share and contribute, please. This is meant to be semi-social, so go ahead and answer, say your name and stuff like that. Let's see. Where is it posted? It should be posted in Canvas, and it should have gotten emailed to you today. Let me look on Canvas real quick. I'm pretty sure it's on Canvas under Files. If it's not, I will put it there now. Let's see. You should have gotten an email. All right, yes, I will remember to do that. Let's see, this is this class. I'm double checking to make sure it's in Files. Under Activities. Chirality, yes, it is there. Oh, let me publish it. That's why. Publish. So it's also available under, oops, under Canvas. Wait, hold it. No, it unpublished it. Okay. Publish, update. There we go. So if you didn't get that email, it's in Canvas as well. Okay. So let's see, I'm looking at the questions here. Where is it posted? Got that. And then how do you want to number the answer if we're using notebook paper? Oh, that's a good question. Okay, so let me go ahead and, no, why am I sharing that? Okay, stop share and reshare. There we go. Let me share my screen. Adobe Acrobat. Okay, so the first page is going to look like this. So the first thing you do is you see if it has 4 things. If it has 4 things, assign it R and S. Okay, do whichever one you like. I prefer my hand one, but if you like to draw it, go ahead and draw it. I would, again, redraw them all such that the lowest priority is facing backwards. There's also a copy of the group activity posted in the chat room if you don't want to go all the way to Canvas for that. Okay, so so what I would do is if you're going to just put this on notebook paper, is I'd arrange them in the same order, and so that you would have your boxes arranged in this pattern right here, and then I should be able to figure it out. The second one is you have 6 boxes here, and all you're trying to do is assign R or E or Z. Okay. So remember, with E or Z, you're going to assign priority to one half of the double bond, assign priority to the other half of the double bond, and compare the two. You do not have to assign 1, 2, 3, 4. You only have to assign 1, and then assign the highest priority on the other side, and then look for, are they on the same side, which is Z, or are they on the opposite sides, which is E. Okay. All right. So that's our assignment here. And that's how to answer if you're going to put on notebooks. So after your breakout sessions, we're going to have the full time available, the rest of the time available to us at 1:50 to work on this. If you're done early, go ahead and just leave. Upload it to Canvas. You have to have it in by midnight tonight, okay? Right now we have 62 participants, so that's going to give us about 12 rooms. And then I'm going to have to move a couple people around. So I'm going to go ahead and start. Let me stop sharing. And I'm going to assign some breakout rooms. Okay, so just go ahead and accept that into the breakout room, and a couple people I'm going to move, so just bear with me. I'm going to go ahead.